Okay, so we talked about this at the end of last class, the idea of arc length. In BC calculus, you cover two-dimensional arc lengths. You're calculating little, the lengths of these segments, and then you're chopping it up more finely, and the sum of those little lengths is going to approach the actual arc length. You've seen things that look like this before. This should not be too new for you. The arc length formula for a two-dimensional shape. For this first one, though, one limitation right here is that what form does the equation need to be in order to use this, or what form does the equation need to be in for the curve in order to use this formula right here? Y equals something in terms of x, right? As we go further and further into multivariable calculus, not only are we adding in another variable, sometimes we don't have functions. We have parametric relations that could fold back on themselves, right? So this isn't always going to hold. So in BC calculus, you might have seen this second formula broken up into what? Do you remember? Maybe you kind of remember. Yeah, you're writing x in terms of t and you're writing y in terms of t. You do some rearranging. You do a little bit of rearranging and you end up with, I think I wrote it down here, right here. You end up with this thing right here. Now, why is that equation useful right here? Why is that one useful?
What are alpha and beta?
It's supposed to be A and B. For some reason, I kept on writing alpha and beta. I don't know why. When I originally wrote this, I was writing alpha and beta. It's just A and B. It's time equals A to time equals B. Sorry. Why is it useful to have this equation?
You can put it both in x and y.
Yeah, you might not have it in terms of x and y, right? You might have it in terms of t. You might have it defined parametrically, and sometimes is it always easy to transfer between the two?
No.
Oh gosh, no. Sometimes you have to break it apart into some ridiculous number of functions. Functions are really limited. Relations are less limited, but sometimes you're going to have one as opposed to the other, and it will be much easier to deal with the type you have. Absolutely. So what's the arc length from 1, 1 to 4, 8 of that? And this is not a function, y squared equals x cubed, but we're looking at one section of it. So if I wanted to find the arc length, if I wanted to find this length from 1, 1 to 4, 8, what would I need to do first? Someone raise their hand and tell me. What would I need to do first? You don't have to take the derivative first. What could you do even before you do the derivative? Yeah.
You square root both sides.
You could square root both sides. And well, if we do that, we're breaking it apart into two functions. It's y equals the square root of x cubed and y equals negative the square root of x cubed. But we're only dealing with this part right here, this positive arc. So we can really just deal with that one right there. What's the derivative of that one? What's y prime equal to? So 1/2 x cubed to the what power? Negative 1/2 times what? 3x squared. So let's look at our formula here just so you remember. So we're going to use this one right here. It's from a to b. Now when it's from a to b, so what's a on this one? What's b?
1 and 4.
So it's going to be 1 to 4 of the square root of 1 plus this thing squared, right? Do you remember one thing I asked you yesterday repeatedly? I asked you, can you always integrate things like this? What do you think?
No.
Sorry, I'll be more specific. Can you always integrate things like this by hand?
No.
No, not at all. There's two things that you hope. If I gave you something that vaguely looked like this and asked you to integrate this by hand, you would hope you can do one of two things. What's one of those things you hope you might be able to do? It might be some inverse trig function, right? And you might be able to substitute inside some inverse trig function, right? Do some creative substitution and then go, oh, cool, the answer's 5, right? Okay, so inverse trig functions might rescue you. What else might rescue you? What method for integration might rescue you?
Parts?
Yeah. Use substitution integrating by parts. Those only work in very specific circumstances. What do you suspect? Do you think it's going to work in this circumstance?
Yes.
Really?
Well, the book gave it to us. Don't you have to square that thing?
And we have to square this thing. Yeah, exactly. So is this something? Okay, yes. If I just gave this to you right now, could you clean that up for me? What do you think? If you think you can do it by hand, take a minute and try to do it by hand. But if you can't, what should you stop and do?
Okay.
Use the integrate function on your calculator. Please try that, okay? Some of these are just not meant to be done by hand. Is that okay? I think you live with sometimes a false sense of security because you spend so much time only doing things you can do by hand, integrating and differentiating. is it always the case that you can anti-differentiate or differentiate? No, some nasty, nasty stuff, right? I mean, I can change things like this, like x equals e to the x minus 2. Solve that by hand. No, seriously. Do you have any idea how to solve that by hand?
No.
Okay, out the door to the back. Grab your backpack. Yes. If I make small changes to really well-known equations, do they become really, really, really hard? Yep. Like, I'm serious. Try to solve that. Try to solve that. Not right now, but like write that down. X equals e to the x minus 2. It does have a solution. Can you graph it and find an intersection? Yeah, it does intersect. So there is a solution, right? Can you, as high school algebra, like calculus and below students, can you figure? No. It's really hard. It's really, really hard. Point being, if you get to something like this and you need to use your calculator, go right ahead. Are you all familiar how to do that on your calculator? Integrate on your calculator? Yeah. You should. If you don't, look it up. Label. So it says this. If you're going from time equals A to time equals B, and you have a three-dimensional, you have a parametrically defined function, you have f of t, g of t, and h of t, it's a pretty is that pretty clean in terms of formulas? Mm-hmm. That's ridiculously clean. It also summarizes to this. L is the integral of the magnitude of what? The derivative of r. Exactly. The magnitude of the derivative of r, right? Because to get the magnitude, you square it, right? And then you take the square root, you sum the squares. So that's kind of nice. That's the shorthand way. So you'll see that written. Instead of writing this whole big thing, they'll write this instead. Because what is r of t?
That.
F of t I plus g of t j. That. Exactly. That will the derivative of that. Exactly. Exactly. So that's just shorthand. Okay. So let's look at what comes next. Clip this in. Two things here. There's an example I want us to do and something first. Here, let's take a look at that relation right there. Let's look at the bottom half of this first, right here. What's the relationship between these two space curves right here? Can someone tell me the relationship between these two? Here's R1 of t and R2 of u. What's the relationship between? Raise your hand and then tell me what the relationship is between the two. When you have, don't say it out loud. Nope. 0 to 2 pi. How do you know it's 0 to 2 pi?
Because that's the only one that changes.
Yeah, look at this one. There's t. It goes from 0 to 2 pi, exactly, of the square root of what?
Negative sine t squared.
Negative sine squared t, right?
Cosine t squared.
Plus cosine squared t. And it's not actually, that's incorrect. I need to do this, right?
Yeah, and then squared.
And then squared. It makes a difference, right? Because it's going to be positive. Is that a key difference?
Yeah.
Oh, come on. How many times do you remember doing trig identities and like that one negative sign killed your entire thing? I remember that. Plus what?
Plus 1.
Plus 1, yeah. Well, what is that?
That's 1.
So this L equals 0 to 2 pi of the square root of 2. And it's what's on the outside here? We're missing something on the outside.
dt.
Ah, yay, dt. Yay, dt. So what is this going to be? L is 2t, root 2t times what? From what to what? 0 to 2 pi. So what's it going to be? 2 pi root 2. Yeah, there it is. Absolutely. So sometimes do they work out nicely? Yes. Was that purposely set up to work out nicely? Yes, it was. So we have this. S of t is going to be arc length. So distance, arc length is going to be from a to t, r prime u du, a to t of that. Yay. Wonderful. Wonderful, wonderful, wonderful. So what can we do with this? Usually we have s in terms of t. And usually we have r in terms of t.
R is
is the definition of the space curve. How we're defining the space curve, how it's traveling.
And S is the arc length.
S is the arc length, exactly, right. So we're getting arc length based on t, and we're getting the position based on t. If we could reverse this, instead write it as t in terms of s, you can take this and plug it in where? Right there, and now you have r in terms of s. You have position. Yeah. Position as a function of arc length. If you can write that, you're able to find out things like where is the bug after a certain amount of time. Usually it's been pretty easy for you because you've been dealing with lines or a circle, parts of things that are really easy to find the arc length of. But now can the space curves do really crazy things? They can do very, very crazy things. So let's do some example questions. Yeah, exactly. S in terms of t all the time. But what does t equal? S over what? Root 2, exactly. So what is r of t of s going to be? Yeah, so it's going to be cosine of, you remember the original equation is up here. Here's r of t. So instead of t, what are we plugging in for t? S over root 2. S over root 2. Here's the original equation. I'll clip that in. So here's the original equation, but instead of t, what are we writing? S over root 2 plus sine of S over root 2 j plus S over root 2 k. So that's the position in terms of arc length from where? 1, 0, 0. Why did we need the initial point 1, 0, 0? What did that tell us? If we know we're starting at the point 1, 0, 0, but we have it defined parametrically, what can we find from that? What is t when you're at point 1, 0, 0? What's time equal to? If you're at 1, 0, 0, time is equal to 0, right? So what this means is S is the arc length from time equals 0. So if you're starting at 1, 0, 0, time 0, and you go 3 units, we can find out exactly where we are by plugging it directly into this equation. We good so far? Your brain melted a little bit? So let's do a little reading time here. A parametrization RT is called smooth on an interval if, we talked about this before, if R prime is, oh, this was an AB calculus, sorry. It's smooth if R prime is continuous and,
No, that was
oh, is our class? Sorry, 2 calculus classes messing me up. It's smooth and the derivative can't be 0. A curve is called smooth if it has a smooth parametrization. So if your parametrization of the curve written in parametric form is smooth, then the curve itself is smooth. Yay.
So you have to write it in, you have to derivative of it.
You could, yes, you have to take the derivative. That's correct. And then show that R prime is not going to be 0 anywhere on the interval that you want to show is smooth. The curvature of C at a given point is a measure of how quickly the curve changes direction at that point. Why isn't this as simple as just taking one derivative? You have several dimensions. Instead of just going up or down, this thing could be going kind of up and over, to the left or the right. So it's a measure of how quickly it's changing curvature. It is the magnitude of the rate of change of the unit tangent vector with respect to the arc length. A smaller, this is how you can think of it, everybody, okay? I'll say this out loud. Smaller circles, do they have a higher curvature than a larger circle? What do you think? If you're looking at a smaller one or a bigger one? Smaller one's going to have a bigger curvature because it's changing, what is it right there? Of how quickly the curve changes direction. A smaller circle is changing direction faster than a larger circle. So this is a measure of how quickly it's changing curve. So that's the nice definition, the curvature K. Now, does anybody know what that is and how you say that in Greek? Does anybody remember? K.
Oh.
It's just K. No, I don't know. It's kappa, maybe? I forget. I actually don't remember. Many of you take notes by just writing down whatever's inside the red box, which is fine. So here it is. This is what you need to remember for curvature, everybody. Curvature is equal to the magnitude of t prime t over the magnitude of
R prime T.
r prime t. What is t?
The unit tangent vector.
The unit tangent vector is just, if you're on a roller coaster, it is at that point like where you're headed, right? What's r prime of t going to be?
The rate of change of position.
The rate of change of the position. Do you want to do one of these?
Yeah.
See what we're doing? Let's do one of these. Yes.
But isn't unit tangent vector?
Sometimes you get clean answers, sometimes you don't. Yep.
You have 0 curvature.
Okay. Are you okay with that?
Yeah.
What vector is?
That is a
Principal normal vector.
Normal vector.
Yes.
But why does it always go in instead of out? It doesn't really matter.
That's a very good question. Why does the normal vector go inside the curvature as opposed to outside the curvature? Let's revisit that in a second, okay?
Oh,
That's n of t. Do you agree with that?
Yes.
Okay, so what was your question?
I was just asking.
That we just did? This only works if it equals a
That's what I was gonna
constant. This whole thing falls apart if you're not dealing, if this is not, this is a, these are
draw a circle.
both a unit vector, okay? And this is a unit vector. And that equals t prime t over what? Just go with it for now, okay? Like this. Okay, I need to add in one more vector you need to learn in order to be able to answer.